Okay. Hello, everyone. Well, thank you for joining us this month. I'm John Cazalla at the Telco OCP sub-project call. Today, we got a special guest, Dirk Blevins. He's going to talk to us about MHS. And we've been kind of talking about this a lot in the Edge group as well as the Telco group about how we can kind of take modularity to the next level. And kind of what's been driving the interest is adapting the edge form factors to not only support, say, a flexible chassis, but then also the componentry inside. And so we've talked quite a bit about MHS, and we're just really glad to have Dirk join us and give us a much deeper dive than probably any of us could give justice. So with that, I will go ahead and turn it over to you, Dirk, and take it away.
All right, thank you, John. Thank you all for having me today. I'm Dirk Blevins from Intel Corporation. I am a one of the leads of the data center modular hardware system specification, modular Dino specification. I also lead what is called our shared infrastructure work stream. I'm a co-lead for that. Um, and I'm also a co-lead for what is just recently came about called our Edge modular hardware system work stream as well. Um, Today I'm hoping to be able to share with you a little bit about what MHS is about as a whole. Um, and then from there, see if I get this to move forward, talk a little bit about what we're thinking about from an Edge perspective. Obviously, it's in its infancy. So it's going, we're learning, and obviously feedback is really welcome, especially from this group, because I think what you'll see from the presentation is that the intent is around building what I would call pieces or Lego blocks to allow you to be able to build solutions for telco and telco's infrastructure. And then finally, I hope to take maybe the first half an hour or so and go over that material. And then the last, 20 to 30 minutes, let's just have an open discussion on what you've heard and then understand, how this might fit, how, where we may be able to make it adaptations and then possibly some collaborations. So when we look at what's going on of the structure and the way things are looking to shape up, now we haven't finalized this, but it's moving in this direction, and I do believe this is the way it'll end up being. Is that what's going to happen and take place is that the DCMHS sub project will likely be renamed to the MHS sub project, and then underneath the MHS sub project, essentially you will have the DCMHS work stream and you'll have the Edge MHS work stream. Now, with that said, what we want to do is we will be doing different developments, and in the first development primarily out of the Edge MHS work stream is going to be just HPM work. So that's why we haven't taken and had any substructures. But the more important thing I want you to notice is that the intent of what we're trying to develop is to get essentially scale capability from connectors, from ideology, from form factor, fit, function, with all these solutions from pieces where it makes sense. So if the 60 millimeter supplies make sense from MC or PS, we would want to leverage those in the Edge work stream, as well as leveraging those essentially in the data center work stream where they're applicable. Same thing for different power connectors or riser connectors or things of that nature, because the more scale that we have, the cheaper that these components get, the easier they are to find, the easier to find supply, et cetera, et cetera. So that's essentially our intent for the way that we're organizing this. Now I'll show a couple other things in a couple slides in the future, how other pieces play into this. Now, interestingly enough, for the HPM pieces right now, we have three different HPM substructures that's going on. One is our full width substructure, which this is, you can think of this as what would be like a traditional 19-inch rack mount server that you would see from many different vendors that exist out there. To name a couple of them down here on from the contributors list from the CLA members, like a Dell or an HPE, like a Power Edge or ProLiant server. So this is a form factor that is optimized to those types of servers and server environments. Now, they can be used into cloud and data center environments as well. But their primary focus when we came up with this was those enterprise class servers, be it 19-inch or 21-inch. Then we have the density optimized solution. Now, when we started this, we were thinking about, single node computers, essentially. So one socket computers that would be out there. We were also thinking about telco equipment, short depth, short chassis usages, things of that nature. And when we started building this, that's where the density optimized name came from, was because we were trying to say, hey, we know we need to fit into some really short depth solutions in order to be able to make these products be able to work in these environments. So that's where this came about. Then what we've evolved to is what's called the scalable density optimized. And I'll explain in a little bit more detail what that is. I've got a couple slides that talk about that in a moment. But the scalable density optimized is to create a series of HPM building blocks that can scale from 19-inch to 21-inch to some really short depths to some really, elongated, more feature-rich solutions as well. So when we look at those kind of environments, essentially that was our target, to be able to create a more scalable HPM system of equations. Now, with this said, we do believe that there's still some gaps in these HPMs, and the HPM stands for host processor modules. I like to think of it, because I'm old, I can tell by my hair, I like to think of it as like a motherboard in the traditional sense, but there's going to be some gaps in where that's at, and that's what's kind of driving some of the edge MHS work, because we do believe that we will need to get shorter. Some of the things in the DCMHS are not optimized, and those are things that we want to further optimize. Finally, you can see there's a good list of CLA members that are contributing in adopting these specifications and publicly, driving these specifications. So it's a good group that's been involved with trying to develop these solutions. Now,
so just a quick question there. So with the Edge MHS work, you said it's really kind of being driven from an optimizing kind of approach. Is it also looking at like these environments? Is that also
absolutely?
Okay.
Yeah. So more thermally constrained environments, out at the far edge, the types of workloads that may be going there and the needs that's associated with that, all those kind of things. And I got a slide on that in just a moment too.
Okay.
Well, hey, Dirk, so I think what John's driving at is that the edge, while we used to call it the open edge because it focused on that server platform for the far edge solution for a 5G situation, that group has now evolved to just be the edge group. And it ends up being, we attracted some attention from some of the folks who wanted more ruggedized form factors. So we've got people with ship side of the railroad tracks, on the trains. We even have now gotten some people with satellites talking about a form factor. So when John's talking about the environments, I think we're not talking traditional telco type environments that we were looking at for far edge. But the edge group is now kind of expanding its scope somewhat at more edge applications. But typically there are some kind of environmental factors, ruggedness, for instance, or temperature, or that kind of thing.
Yeah.
Just
so
with that, kind of how we're evolving somewhat, I guess.
Yeah. I completely agree. And certainly the first thing that we want to chew off, if we look at this picture, I'll go ahead and hop here since we've moved down this path.
Sure.
Our initial focus is going to be on this environment, which would be kind of a portion of the near edge through a portion of the far edge. You can see we start to get into, like smart city kind of environments where you have pole mounted, solutions and things that would be out in the system. This This could even be a rail solution, depending upon what you're doing in those particular environments. So we're starting to consider these kind of things. Now, what we haven't taken as a focus of the CLA at this point in time, Craig, is looking further out into like an industrial appliance or something that may fit into a transportation device or actually on a rail car. Do we think that eventually we may be able to get there? I think there's members of the group, and certainly I will speak for Intel. I think Intel has a vision that we can further extend this out into this region. But much to the point of this slide, as we move further and further away from the near edge, the requirements and complexity start to diverge. So it becomes more difficult to create standards and specifications for differentiation purposes. So, but we do believe there's some opportunities there. Our initial focus is going to be into traditional, what I would call telco, more in this blanket area, and then starting to look at like some of these smart city type environments where you would take essentially the same HPMs that might go in this server or in this server and be able to use it in this type of an infrastructure, if that makes sense.
Yes, sir. Yes, sir. Thank you.
So going back to this, it's kind of good that we went there because it kind of starts to explain a little bit of what we're trying to do with the whole MHS effort. If you look at the current model that essentially exists today, everything's essentially a bunch of different vendors that are producing different products. But then there's a bunch of monolithic motherboards that people build a bunch of monolithic appliances. Intent of what we're trying to say on the right-hand side is that wouldn't it be great if we had some common building blocks, Lego blocks, for lack of a better term, because I love Legos. But with that said, you could take and use the same Lego blocks and still be able to build differentiated solutions, satisfying these different opportunities. And by doing that, it allows the system vendors, like some of the folks that's on this call, to be able to put their focus on their differentiated aspects, and then let the other elements that are generally the same between the designs anyhow, be able to be leverageable across different solutions. So you may see, the same HPM from, company, A into all three of these designs. And you may see the same HPM from company B into all three of these designs. But it starts to allow a level of synergy that allows more products to be consumed, more things to be consumed faster, and allows additional innovation to occur, because now you're not necessarily resource constrained designing all these different independent motherboards from all these different CPU vendors. I think it also creates more variety in the marketplace by not forcing companies to have to pick and choose from the different types of silicon, because they can build different platforms and reuse different pieces, building blocks. Regardless, you may, for instance, your riser substructure on a design might be the same, whether it's, I'm going to throw Intel, AMD, or Ampere, or NVIDIA down here, if that makes sense. All the rest of the system may be the same, but the HPM may be the only thing that is essentially changing. And there's huge power in that. So does that make sense of our goals and intent?
Yeah, absolutely.
So what are these things? This is more so just to give you a high level of what we're doing. I kind of looked at it from a HPM as the heart of the system of where things go. As I explained, we have the full width, the density optimized, scalable density optimized. And then from there, there's these other building blocks or Lego blocks that come around, that go around the system. Be it the plug and play is a new one that's coming about. And I wanted to talk about that for just a second, where it starts to take the different hardware building blocks that we've been defining essentially, and now they're starting to define the firmware layer, so that as these different pieces get plugged in and out, these things can truly eventually become plug and play. Now there's a crawl, walk, run phase to this, obviously, to make this happen, but that's essentially where we're headed, with these solutions. The shared infrastructure is to define a signaling interface to allow like backplane and midplane connectivity to start to become more common, because then it makes things like the plug and play scenarios easier to be able to achieve. Now, that doesn't mean that the connector will be the same. We've intentionally steered away from the same connector because, as an example, let's go back to the open edge comment you made a minute ago. And I'm going to use a different specification body, the ODCC, where they have the OTII and the OTIE specifications. They use different high-speed backplane connectors on the back side, but the signaling is essentially the same between the two different specifications. They're pretty close between between a lot of different specifications where there's crossover. So, for instance, the Open Edge was mostly a management interface. If you go look at those other specifications for their management interface pieces, those things are pretty synergistic between the types of signaling that goes on. So we're trying to keep the signaling level to allow these specifications to become more synergistic and more easily consumable. Finally, there's a piece here that we also leverage from other groups. So we also leverage the secure control module from the hardware management group in the OCP and the OCP NIC from the NIC group as well. So these are important pieces. This is some look at some of the presentations we've done in OCP. This is the ones that I think I don't remember if it was John or Craig mentioned a minute ago that we were presenting out at the tracks out in San Jose earlier. But you can kind of see where we're at, and you can see where the specifications are trying to drop at. The Estino 0.9 is actually already out there. And MSIF, we're looking to drop in Q3 for 0.75, trying to get the 1.0 by Global Summit is the target. And then the edge work we're starting to look at around essentially, to go to the next slide, the pieces where we see we've already identified that we need differentiation, which is a new style of SCM, because that coplanar SCM is really painful to deal with in edge solutions, given the physical form factor of those things. So we've been exploring some different possibilities there in the edge work stream. So if any of you all are part of that work stream, I believe it was the meeting 2 weeks ago that Intel presented the original Dell proposal, and then we went from there into the Intel counter proposal to that 2 weeks ago. So if any of you are part of the SCM work stream or have access to that, you can go back and review that as well and kind of get a feel for where we're headed or what we're trying to do. And they're very similar between the Dell and the Intel proposal. We just made some minor suggestions. And then the HPMs obviously will need to change, and I'll explain that in a second. So the Edge group is going to really be focusing on these new things that are required, predominantly for telco edge in the initial phases, but then again trying to look to a further edge set of building blocks in the future. So this is just kind of a pictorial view of the pieces that are common between different HPM subsections that exist under the MHS umbrella. And you can see that we have the XIO, the PESTI, the PIC, plug and play, the CRPS, the NIC, and SIF that is usable across, be it either DCMHS or Edge MHS. And then from there, these HPM types can be utilized in order essentially to be able to then leverage to build different products. So if you look at these solutions, data centers predominantly focused on enterprise hyperscale solutions, where the edge are looking more towards traditional edge solutions, IO, all front facing, short depth, some pole mount stuff, as I mentioned before, things of that nature that we're trying to look to capture with some different sizes that may exist out to go into these different environments. The intent is you can mix and match all of these pieces in order to build differentiated servers that exist out on the right side. Does that all make sense?
Yes.
Yes.
So I want to quickly go through what Estino is and give you a high level. So scalable density optimized, we wanted to create a scenario of, basically designs that are, um, a matrix of solutions that are either 19-inch or 21-inch or half width or full width, and it creates some scalability between the different designs. So we came up with this notion of 4 different sizes that are creative, basically based upon those different criterias in the Carnot map. If you look at that, there's the Class A, Class B, Class C, and Class D boards, where you could see by looking at the outside edges what they are optimized or targeted for, essentially for the various designs. Now, if you look really closely at these things, and I'll show it in the next slide, but the risers and all the I/O and things of that nature essentially are common between the different designs to allow these solutions to be able to scale in width and or length, and be able to be reused within essentially a common chassis. So if we go to the next slide, you can see that looking at the picture on the left-hand side over here, that let me go to my laser pointer too. If you look at this picture on the left-hand side, essentially we have a Class A 305 length board that you could actually have a 305 or a 335 length board. And if you build a chassis, let's say we build a full width chassis for fun, there's a 21-inch wide chassis, then you could drop into this particular solution seamlessly with all the riser placements, all the rest of the infrastructure essentially the same between the different designs, either a Class A or a Class B board by itself, or Class D board by itself, or you could drop a Class A, 2 Class A boards by themselves, a Class A and a Class B, or 2 Class B boards by themselves, all into this solution. The power of that particular scenario is that it allows you essentially to be able to create, cost optimized solutions in a very easy fashion, for different price performance variations that may be able to exist essentially out there in the marketplace. By doing the scalability, we have fixed widths, we have scalable lengths, and by doing that, then we also don't force ourselves into a situation to where the specification is obsoleted too quick. So if we know we need to grow the length beyond 335, it can grow on to be a 355 if the CPU complexes or the high speed signaling or whatever starts to require more physical real estate in order to be able to support the solution. So we've created an environment with this specification that allows us to continue be able to evolve this specification over time, also have some level of backwards compatibility with solutions. Now, one of the things we didn't do, and this is really important, is shown up on the right-hand side, is that we looked at trying to maintain compatibility between all the classes. It really became quite difficult. And interestingly enough, where it became quite difficult from was the bottom side keep out scenarios for things like retention hooks or placements and keep outs for those kind of things. Because of that, we said that, we're going to do our best to maintain as much compatibility between all 4 types. But the goals that we're going to guarantee are compatibility between A, B, and C, or A, B, and D. And that's really important. We did develop some methodologies to where you could come up with some, field movable retention hooks on the bottom side that would allow you essentially to be able to make all these solutions compatible. But that adds more expense to the solution, and we felt it was a pretty easy exercise for system providers to be able to do that if they so chose to do that. So this is an important point, these points around SDNO and where it's headed to, and why we deem this as being quite interesting from a solution standpoint. I do want to say that it does not obviate the full width or the DINO specifications, and we tried our best to maintain compatibility with Dino 200 and basically 210 millimeter solutions for the width of the Class A boards wherever possible. There are some mild differences. Chassis can be built where it can accept either board.
Have you guys looked or thought at all about liquid cooling and if that would impact this in any way?
We have been thinking about liquid cooling as we're defining these things.
Okay.
And that was one of the reasons why we wanted to recreate the scalable link scenario. Because when you start to think about liquid cooling, if I go over to the picture on the right, you start to have keep out areas for mounting locations and things of that nature. So we actually have developed a lot of models to be able to showcase how you would essentially implement liquid cooling in these environments, predominantly, and that would be predominantly cold plate scenarios that we've been focused on there, not immersion.
Okay.
But our scenario has been cold plate, and it's been into solutions to where understanding the nozzle sizes, that would be required for the quick couplers, how power is delivered, where it's delivered at, all those kind of things for both 19-inch and 21-inch, as well as building out very detailed models to the point to understand exactly where, as I was saying, the dim cooling apparatus, mounting apparatuses would go, as well as the heat sinks mounting apparatuses, and then all the way up to actually the add-in cards or the riser cards. So it's absolutely being considered as we're building this.
Great. Thank you.
It's a great question, by the way. So I kind of talked about this slide already. I'm gonna move on through this one to the next one. And this is just talking about some of the things that of traditional telco that's driving the need for these shorter solutions. There's a legacy install base that exists. A lot of those solutions are between 450, 480 millimeters deep. Other solutions are 600 millimeters deep. This starts to limit the depth of the equipment per the specifications. For these chassis specifications, you can go as deep as 310 millimeters to the back wall in these 450, 480 millimeter chassis, and as deep as 450. But those chassis were traditionally designed for side-to-side airflow versus front-to-rear airflow. And because of that, starts to play into the aspects of the cable bend radius and what the requirements are there. And what people have traditionally been doing is going as deep as 450 and then taking this extra 150 that exists here, coming off the back wall, approximately 30 millimeters, eating into this cable bend radius location, and then allowing front to back airflow to occur with essentially a plenum in the back to be able to escape the air in the solution. So these are the kind of things that need to be considered as we're building these solutions. In addition to that, the types of power, you need a provision for AC and DC because there's different powering environments that exist in these solutions. We need to make sure that we have the ability to comprehend both of those scenarios. So what are we thinking and what are we looking at? So and this is really an Intel perspective, although we've had some of these conversations in the group, but this is kind of where Intel is where we think things need to end at, and this is what we're going to be trying to drive into the work stream. But essentially, we believe there's three predominant depths that exist in these systems: 310, 350, and 430 is the ideal length of these solutions. With that said, we want to be able to leverage, essentially a hardware system for the edge. We want to have compatibility with DCMHS where possible. And we want to be able to design into different environments, be it a pole mount environment, be it a traditional telecom environment, all the way into rail equipment, very industrial computers, PCs, in manufacturing environments. We want to be able to do that and have that capability. We do believe that optimization around 19-inch racks are really important. We don't see much in the 21-inch stuff being utilized currently. And then from there, we want to use these things to start to pre-solve a lot of the technical challenges that may exist. So Intel, obviously, as we normally do, will start to work on different solutions to try to build out some of these things to prove the specifications out, with partners and things of that nature. So what we're showing at the bottom, essentially, this is my last slide. It's some environments of what we see for like a 310 millimeter deep solution using MCRPS supplies. It's going to be used in like a VRAN environment or a SASE UCPE type environment, or an edge server doing even some AI infrastructure, depending on what you're wanting to implement. Then over to the right hand side, these are some models showing a type A and a type B used in an infrastructure or solution. And this is showing a 3-node, but it could be a 4-node to a U solution. We do have this notion, and the reason why we're sizing these things in around one, I've got a 162 and a 168. Intel's view is that we believe the number is somewhere between these two numbers. So we kind of made this one smaller to show we believe is the smallest we could envision building something. And we don't believe going much beyond 168 is good, because once you start to do that, you start getting into a scenario to where you can no longer do 4-node 2U, which we think, and still have a chassis manager, which I'm showing, kind of a different kind of thing. I know in Open Edge there was the RMC that was there, but this, you could kind of think of this like the RMC built in a different form factor in this style of design that we're showing here. So with that said, that's what I had to present today. I'm going to pause, and we'll just open the floor for discussion. John, Craig, and team, if that works.
That sounds good. Yeah. So one question is, so we're seeing a lot of workloads that are going to start driving a lot of, say, GPUs and accelerator cards into this edge. We've been kind of flipping this whole equation on its head, where originally everyone was looking at trying to make these edge things smaller, lower power, lower heat, all that kind of thing. But now people are wanting to do like augmented reality, virtual reality, AI things, and we're kind of seeing that okay, we're gonna have to put maybe some accelerator cards in here. So that's kind of where the liquid cooling question kind of comes in. What are your thoughts around those things, and kind of this approach?
I certainly think that we're seeing the same types of requirements that people are driving. If you notice over on the right-hand side, we are trying to put in facilities to allow, like, add-in cards to be placed into these solutions. Interestingly enough, some of our thermal solutions are yielding much better results from a simulation standpoint than what we thought. So we're starting to see some better scenarios. One of the things of trying to architect this to allow like a 1U and a 2U environment is, though, get better air-cooled thermals as well, to allow us to do things like higher temp CPUs that may have GPUs integrated in them, or GPU functionality that's integrated in them, different accelerators, as well as potentially additional add-in cards, because retrofitting some of these environments for liquid cooling is going to be a challenge at the some of these edge locations. But we're also not precluding that from being done. So that's, by provisioning these in the way that we're doing it, we're trying to ensure that we're making allowances for those kind of things. Now, the big thing that's going to be driven, though, is that when you start to do those things, you start to take up room essentially in the back of the chassis, because now you're having to add infrastructure for your quick couplers and and your liquid cooled pipes to be able to feed down to the different elements in the solutions. So we know that you may have to start to reduce the size of what, for instance, you might have to use a type A board, liquid cooled environment, to where you want to use a type B, kind of thing in an air cooled environment. So those are maybe some of the trade-offs that you have to start to consider. So, does that make sense?
Yeah, thank you. And maybe one other question from, and this is, I'm trying to remember things that we had from our group discussions. In the telco environments, we have kind of these shake tests and some of these other things. There was some concern about the connectors and things that are used for MHS, if they would be ruggedized enough to withstand those kinds of nibs testing and that kind of thing. Do you have any thoughts on that?
Do we know which connectors that we're looking at? Is it the riser connectors like the 1033, or is it the power connectors, or all of the above? None of the
Yeah,
above.
I think probably all of the above. They didn't. It wasn't specified. It was just there was some concern. Did MHS are these connectors ruggedized enough to withstand kind of some of this NEBS testing, or should we look at that, from a telco perspective, or is it maybe we just kind of take the connectors, test it, and see what happens?
Well,
that was kind of around those lines. Like, do we need additional requirements there? What that was kind of, I think, the group wasn't sure.
And there's different classes of NEBs too, so that brings in another variable into the equation. I certainly do know that NEBS has been discussed in the work streams, and that certain system vendors are looking to do certain NEBS certifications with their systems using those connectors. So I do believe it will meet certain criteria with most of the connectors that we have out there. To say it'll meet full, what is it, level 3 class 1 or whatever it is. So I mean, I said that backwards. Yeah. Class 1 level 3, but I don't know that I have the answer to that question right now. Okay. But what I will say, though, is that's a portion of something that we would probably want to discuss, and that's good feedback. I know, Susan, I didn't notice if you were on the call, but take that as a note that we probably want to roll back, that understanding NEBS is going to be important in these environments, and that we need to make certain that the connectors that we do choose to leverage are NEBS certifiable. And then secondly, if they're not, what do we try to drive as an alternate solution?
Okay, got it.
Yeah, I think that was kind of like the big kind of question. And if there's things that us from the telco group or the telco edge group could help kind of contribute or participate in helping look at these things, or giving additional requirements or whatnot. I think that was kind of
I think that would be great. I think if we could come up with a more systematic way to do that and review kind of what we're looking at and get that feedback, that would be fantastic. So
okay.
And maybe in our monthly call we can do that, or maybe we can come up with a method, Craig, to where we just do something more structured just between the two different groups, to where as we're at a periodic rate, we come in once a month and say, hey, here's where we're trending, feedback, are we right or are we wrong, kind of thing.
So. Right. Yeah, I'm much more, the telco side, most of our connectors, get taken out, so to speak, in the seismic test, when you put the system under seismic load and has to carry some traffic while that's occurring. But the thing that's gotten me is a little more of these more ruggedized folks that have shown up, because it's a little outside of our wheelhouse, some of the things that their specifications and stuff, which I think is what John is trying to drive some use cases in the edge group now on, to kind of gather the requirements. So basically, we see ourselves more as requirements gathering people than the designers of the hardware. So what we'd like to do is to develop some type of relationship where we can bring the requirement and then let you guys come back with the solutions for those. You know what I mean?
I think that'd be great. I think that's I think I was kind of heading the same way based upon John's, feedback
Right.
there. So,
Right. I think it's an expertise thing. We don't have the expertise in the hardware that you guys have. And so, but what we've got is the communities of interest that want to drive the requirements or to have their needs, called out, which is something
mhm.
we were missing in the beginning. And the reason for the telco group and the whole thing was, the data center guys could care less about, us telco guys. And so we had to do a lot of this work ourselves with the original like ORV2 systems and to make
Mhm.
those guys and EMI and that kind of stuff that wasn't of interest to them. And so this would be a great way for us to kind of vet those feature requirements and then feed those up and have some, collaboration on those.
Yep.
Absolutely.
I think we got to figure that out and what the right path is there. But I do think it's a good, that would be, I think it'd be
Right.
welcomed,
Yeah, I
so.
mean, obviously, there's a lot of telco, wireless that's represented here, but we're starting, especially in the edge, more than the telco group, that's starting to, branch out and trying to, incorporate more scope in that group.
Yeah. And it sounds like it's even getting broader too, to your point, to maybe industrial appliances, railway, transportation, those kind of things too, to where it's a little
Right.
different environments,
Yeah,
that
well, there was even interesting use cases where we had one where they take this platform into different like geopolitical jurisdictions, and so there would be restrictions on what CPU could be there. So what their requirement was, this needed to be able to fit into a suitcase because they're going out like into far remote areas, and they just need something that they can throw in a suitcase and then just kind of pop out these modules, change out the thing for whatever the geopolitical
yeah. So
requirements
that,
are.
yes, yeah. So if they, if what is it, the Action 79 in the PRC, to where there's certain, only CPUs built in China can be used in China.
Exactly.
That,
Yep. Yep.
that
Yeah. And so like
it may be
and
the
they were
same
talking about.
system. Yeah, but it's just gotta, you put in a new China made HBM in that system versus you know rest of world, for lack of a better term, built system. So
Right. Exactly.
yeah, that
So
makes
yeah,
sense.
we're seeing like a lot of these really interesting use cases of how you would term this edge, and what people are trying to do. And like listen, what they were doing was really interesting because some of these places they were going to, they had very limited internet, and so like these were like put in industrial areas, but they would have to turn off the internet during school hours. So this thing needed to kind of batch up stuff, and then when they get the internet back after school is out, you know, then there was this big data sync that would happen. So it was kind of really these constrained environments and connectivity and cleanliness, dust, dirt, movement, all this kind of stuff.
Yep, yep. I kind of have a little bit of a background into that, but pre-Intel, some a few decades ago, I was actually in military and defense, and uh,
Yeah, that
yeah,
would be another good use case for this. Yep.
yeah. So we were, the shock and vibe stuff, all the stuff. It's just a different animal, I
Yep.
mean, you're shipping something on a rocket ship to space. It's gonna shake,
Right.
You got to make sure you can survive those things, So that's I'm not sure that we're gonna go there, but I get, the point is that there you could be in a fleet, in like a fleet truck, for tractor trailers, and this could be a device there, and there's a lot of
Yep.
vibrations and movement in those environments, and there's a lot of them. There's literally millions of them. That drive around every day, and people are looking to get more intelligence into those solutions. So I certainly get that. So
Well,
Yep.
Dirk,
Yep.
we did have, I mean, we had a couple of contracting companies that were actually working on space applications that have been talking in the past, couple of months. They've showed up and had some pretty strange requirements for, some space applications. Kind of caught me off guard a little bit, once they started talking about rugged environments, and then,
Yeah.
like, oh, yeah, I got you.
Well, it's a whole different animal whenever you start to go there, because now your radiated emissions and everything else start to come into play there. So it's
Exactly.
it's now you got to start to think about physical shielding of the devices and all the devices, and what the upset rate is to all these things, and all those kind of stuff. So it's yeah, I mean, we got to figure out what the commonality is, because I'm sure there's going to be these fringe use cases where it just doesn't make sense. It's still going to be a full custom thing, but those environments love COTS too. And if we can come up with things that work for them, I think we should not preclude them out of the box, so.
Right. Well, I think, that was the part that got me. I'm kind of like you. I would think custom designs for that, but they're wanting these modular off-the-shelf components that they can put together and keep the customization to a minimum, which makes a lot of sense, especially in today's environment, right?
Yep. I know we had a big COTS movement even 2 decades ago, I mean, so it's definitely still there, still an area where they want to go to, and they want to leverage the commercial sector as much as possible. So certainly understand that. Now some of the other challenges that we've had conversations around is that the different types of IO and the variation of the IO. Do we create IO zones and regions into these HPM types? There's a lot of work still left to go on. I'm just looking at the attendees list. I see John Stewie's on here from Dell. And he'll tell you these are a lot of challenges, and there's a lot of variation, and there's even some doubts within the industry. Can we pull off a set of specifications that are ubiquitous for these types of environments? So it's a tall challenge, and if we can get requirements from your group, I think that and some feedback, I think it'll help. Will go a long way. And I don't know, John, if you would want to comment on that or not, but
yeah, it's something we've seen. It's a much more fragmented market. The 19-inch rack made life a whole lot easier for the DCMHS. With Edge MHS, everybody has their own chassis and own ideas of what the depth and layout should be. So we're definitely have a challenge to make it compatible across the industry. We know we're not going to catch everyone in the industry. The question is, can we catch enough people in the industry to make it a worthwhile spec to have? So any kind of requirements or desires on the form factors or any other features in here, definitely let us know.
Yeah. So what else? Is there anything else we want to talk about? We got a few more minutes left. And hopefully John and team, this hit the mark of what you were looking for.
Yeah, I've been kind of hogging the thing here. So if anybody's got any other questions, I don't want it to be the John show. So please speak up.
Hey, Michael, do you have any kind of view? I know with your, you typically are interested in the connector kind of things and stuff. Is there any thoughts that you might have on this?
Not off the top of my head.
Have you looked at any of the DCMHS connectors yet, Michael?
I have not.
Okay, yeah. I'm sure when you start to dig into it, that's when the questions will start to jump up. Yeah. All right. Well, if that's everything for today, that's kind of all I had to present today.
Well, that's been great. Really appreciate it, Dirk. And let's work behind the scenes here and figure out how we can kind of work together. And as Craig said, kind of use maybe the telco and telco edge groups to kind of help channel requirements or give input into what you're all working on. So let's figure out maybe how to kind of get that going, because we're definitely getting a lot of people coming into our groups with these kinds of things, and this is kind of maybe the first kickoff to kind of, I guess, open that discussion and figure out how to kind of work together that way.
Yep, I think that'd be great. I'm looking forward to it and figuring out how we can collaborate. It's always better when we can get this collaboration amongst the different groups. Within the OCP, I think it drives synergy and drives that scale and adoption much better. So I love to see it.
And hey, Dirk, on a telco note though, do you have any kind of thoughts on, say, composable systems, maybe using CXL and how that might go towards either disaggregating or creating new MHS types?
Can I give you a simple yes?
Well, these are some of the topics that have come up, and maybe even some pontification because of your, I think your background would have a little bit more, yes is good, but is that something that we can look forward to in the future, or is that something that we should?
Certainly, I will tell you, at least from my perspective, Craig, and this is all I can say, is as we have been building out the different MHS specifications,
Yeah.
I have been giving strong consideration to CXL and composable systems and how these things could play out. I do think you're seeing some of that starting to evolve with the notion of the PMP group and where that's starting to come about and starting to create these substructures, as well as the SIF group and where it's at. I do believe that there's opportunities for some of these edge systems to take advantage of new technologies and CXL and coherent interlinks between those systems to create a coherent parallel compute environment between GPUs, IPUs / XPUs, if you want to call them, and CPUs,
Yep.
with shared memory in order to be able to create some really high performance systems. I do believe it is a complex coding paradigm, and I think
that's what I was kind of saying from the telco standpoint, because this kind of moves a little bit further, say, from the edge usage, even though it still is the edge, but more the regional edge, where for energy purposes or other reasons, they may want to have a pool of compute resources that are composed and may get recomposed and for different purposes in the evening, or maybe it serves wireless during the day, and then once the people move away from the offices and they go back to their residences, it reconfigures itself, that kind of thing is, but those are more wider, it's not strictly just the wireless edge part, it's more the infrastructure part that's carrying that traffic, the core network, those kinds of things.
Well, that's kind of, I have this notion that I didn't really talk about today of a universal edge appliance, where it just has a set of pooled resources that are available, and they're engines that then you can compose to be able to make them what you need them to be. And I do believe that right now we have not made decisions in the modular hardware system specifications that preclude those things from occurring. In fact, I think we've been very open-minded to ensure that the things that we're doing are considering the advent of new technologies such as GPUs and NPUs / VPUs and CXL and all those things. I throw out some of the craziest ideas, and they tell me to go back in my corner a little bit, Craig.
Right.
But that's okay. That's okay.
So, they all have their day in the end, though, right?
Well, they will. It's not if, it's when.
Right.
And
right.
The key.
That's
so
right. Yeah, if we don't discuss these things now, then it'll take longer, because the more we talk about them, the more real they become and the use cases come, and yeah, absolutely.
Yeah, so I think we're doing a good job there. I really do. I think that the teams are doing a good job at trying to ensure that we have those proper considerations. So,
Okay, great. All right, has anybody else got anything else?
all right. You all have a great one, and thank you for having us in today.
Yes, thank you so much, Dirk. We appreciate it.
All right.
Thank you.
Bye-bye.
All right. Bye-bye.